Hello everyone, welcome to lecture 8 on finite element method. If you think about our lecture on the finite element method, say on ME 362, you can think of three parts into this lecture. So the first part is what I would like to call preliminaries or introduction. Okay? So this is basically understanding finite element method with springs. Okay, so we play with the springs and then we learn everything that we need to learn, or the fundamentals of the finite element method, using just spring combinations. We did the springs in 1D and then we also did springs in 2D. The good thing about using springs is that you have the ingredients of the finite element methods. You have nodes, you have elements, you have assembly. So basically, it serves very nicely to understand the methodology of the finite element method. And after that, you basically go to the finite element method itself, and then we do one-dimensional finite element method first, and after that, we do two-dimensional finite element method. Now, these two are more mathematical, and if you want to think of this course being basically 24 lectures, which almost it is, 1/3 is the first part, which means 8 lectures, so today is lecture 8. 1/3 is the second part, and 1/3 is the last part of this. So basically, this is what we want to do. Today, we want to finish the first part of this. So from the next lecture, we will go to one-dimensional finite element method. All right. So we start this again by having a quick review of what we have done previously in this lecture. If you remember, we discussed about springs, let's say in 1D, and then we mentioned that each spring system can be written as F equals KU. Then based on that, we talked about connecting multiple springs together. And again, we defined global nodes, global elements, and we learned if we have a system like this, and then if you know the stiffness for each spring, how would you combine them? How would you assemble them into a global system? And then it brought us to the global stiffness system that you can see here. But also we learned that that global stiffness that you have is basically depending on the let's say approach that you would take to number the nodes and degrees of freedom in this case. So we discussed that because we have Dirichlet type boundary condition and Neumann type boundary condition, and Neumann type boundary conditions are where the displacements are unknown, we said we would like to sort of order the system or give this numbering such that all the unknowns, they come on top for the displacements and all the prescribed displacements go down. And then if you do that through this process of static condensation, as we talked about, you can come to the system which looks like this. So you can come to this reduced system and you can solve that. And that's what we want to do. So if you solve your reduced system, then you compute all the displacements, and that is exactly the main part of the finite element method. Also, in a post-processing step, usually, if you want, you can calculate the unknown forces. Okay, but that is pretty much a choice. So the first part is what we need to do. That's the most important part. And then we had this new question: how can you sort these degrees of freedom that they do that? And then we learned that by a simple example. So we came to the idea of having an extended node list. And then we said this discussion on extended node list, it doesn't matter if it is 1D or 2D. So we talked about a system like this. And for instance, on this system, you see you have 8 nodes. Okay, so you have 8 nodes. That means you have 16 degrees in total. So 8 times 2 is 16, and 2 is the problem dimension. 8 is number of nodes. Now, that means your stiffness is 16 by 16, but among those 16 components, you can see, for instance, two of them are constrained here, one of them here, one of them here. So basically, you have 4 degrees that are constrained and 12 degrees that are free. So you have 12 degrees of freedom. That means you get a system here which is 12 by 12, and that is all the stiffness that would be later multiplied to, let's say, unknown displacements, and then the additional 12 times 4 stiffness that you have here, they would be only multiplied by the prescribed ones. So this is what we wanted to have. So this would be a nice system to solve, because it gives you that structure that you can, let's say, transform to a reduced system. So this is all good, except that we had to learn how to compute the stiffness for a truss member or for a spring that has an angle theta with the, let's say, with the horizon, with the x direction in this case. And in order to do that, we basically used coordinate transformation. So we mentioned that we know how to compute a stiffness, or the stiffness for a truss in this system in the white coordinate, or in this picture, maybe in this pink coordinate system. So what we need to do is to rotate that into the blue coordinate system, and we do that through this rotation matrix. So we rotated the forces, we rotated the displacements, and by rotating forces and displacement, you end up with 2 rotations which should be multiplied with the stiffness to give you the global stiffness in a rotated coordinate system, or let's say in this case the elemental stiffness in the coordinate system, and you get this one. Okay, so this is the rotated stiffness, and you can see clearly it's 4 by 4, and it has this let's say immediate dependence on the angle theta. Then we talked about simple cases. Let's say if theta is 0, then you have a horizontal element, so you get this 1 minus 1 minus 1. That's what you expect. If you have a vertical element, you also get 1 minus 1 minus 1 minus 1, 1. But now you see this square is kind of shifted towards the y degrees of the system. And if you have, let's say, I don't know, a 45-degree element, then you would get something which looks like this one. So basically, you get more ones and less zeros. So now we know everything. We know how to assemble a system. We know how to deal with springs or with truss members in 2D. And we know how to compute the stiffness for each single one of them. So what we need to do, or what we want to do next, is to look at an example. So we can solve any example like this. This is, for simplicity, a structure with only very few elements and nodes, but everything that we do is extendable to large systems, and you will see that. So we do this by going through these 5 steps. The first step is that we need to number the nodes and elements. Then you create your extended node list based on the boundary conditions and discussion we had. Then you compute the element stiffness, so the stiffness for each element. And after that, you need to assemble them and you need to solve the system. So in the previous lecture, we came so far. We did the first 3 steps. We want to just quickly do the other 2 steps today. So the first thing was to basically number the nodes and elements, and we did this, as you can see in this picture. So basically, based on that, now you have your node list. So you have node numbers, and in front of each node, you have the coordinates x and y. And also you have your element list. That means you have your element numbers, and in front of each element, you have the so-called connectivity. So it goes from which node to which node the element list is connecting the nodes. So that's why it's called connectivity. So let's say here, element 3, for instance, is this element, and it's between node 2 and node 3, as you can see here. So after having the node list, we want to go towards computing the extended node list. And for that, we use the boundary condition information. For each node, we put the boundary condition, and then we assign these, let's say, temporary degrees -1 and plus by adding -1 and +1, as we have spoken before, and then from that we come to this global degrees, and this is the way the system is. So this is our extended node list, and as you remember, it has 12 columns, so 6 times 2 in this case. If it is a 3-dimensional problem, it has 18 columns. If it is a 1-dimensional problem, it has 6 columns. Once you have that, we just introduce those global degrees, so you can see they are in orange colors, in orange. So in the next picture also you will see them in orange. So these are the global degrees for each node. Now, what you need to do is to compute the stiffness for each element, but then you remember now each element has its own connectivity. So for each of them, you can also think of it as basically the XY stiffnesses between the nodes at the two ends of each element. So if you think, for instance, of element 1, so this is element 1. Element 1 is between node 1 and 5. So the stiffness would be between node 1 and node 5. And then x direction, y direction, x direction, y direction, as we spoke before. Now, node 1 in the x direction, it has the global degree 6. Node 1 in the y direction, it has the global degree 7. So you see this 6 and 7 here. So basically, when you calculate the element stiffness, now we don't have to write 1x, 1y anymore. We just write these for now, just for our own reference, so that we remember which global degrees are associated with which, let's say, components or directions in these stiffness matrices. And then if you do the same thing for element 2, you get this. We did this for element 3, element 4, element 5. This is element 5, I suppose. So this should be element 5 and element 6. I haven't written this. Okay. For element 5 and element 6. Now, what we need to do is to assemble all of them into our well, let's say the assembled stiffness or global stiffness. So what you see here is the structure of our global stiffness. And you can imagine that this global stiffness has a dimension 10 by 10. Because we have 10 degrees, you can see the maximum orange number, let's say, that you see in this picture is 10. 5 of them are free degrees or degrees of freedom. 5 of them are, let's say, the constrained ones. So basically what we need to do is to go into each of those stiffnesses and find their corresponding degrees or placement in this stiffness. So to have it more clear, I also number these rows and columns, and these are now the numbers that you see. The numbers are global degrees. Okay, so what I want to do next is to come and pick up each of these stiffnesses. So for instance, I want to pick up the stiffness of element 1, take it to that system, add it to the system, and then go to the element 2, do the same thing, go to element 3, and so on. So this is what I want to do. So I'm going to copy the stiffness of element 1. Come to this slide basically and add it there. Okay, so it's tiny because we don't have enough space, but you get the idea. And to avoid, let's say, clutter here, I'm going to do it element by element. Obviously, it would get too crowded if we do all the elements in one system. But let's say this is exactly what we had. This is the stiffness of element 1, and you have degrees there. So what we need to do is to just put each of these components where it belongs to. Now, in order to do this, let's say, more systematically for simplicity, because I mean, we have this factor 2 square root of 2, and then it makes it complicated. So to have it just more systematic, we are going to write it in a, let's say, in a generic fashion. So stiffness of element 1, eventually, whatever it is, it's going to have 16 components. So it's going to be 4 by 4, as you will see here. Just do it a little smaller so that we get more space. So the stiffness of element 1 is, say, 4 by 4. Okay, and those degrees, again, you can see they are 6, 7, 4, 5, 6, 7, 4, 5. And let's assume that the components of the stiffness itself, they are numbered as we usually number them. So let's say, if we think of this as having 4 rows and 4 columns, like this, this one would be K1, 1, 1. This is K1, 1, 2, K1, 1, 3, K1, 1, 4. Okay, so the subscripts are just the placements of the components. These are like usual numbering for matrices that you have. Then you have K1. You see, the superscript is still the element number. So this is still element number. We keep that. So this would be then 2, 1, K1, 2, 2, K1, 2, 3, K1, and 2, 4, K1, 3, 1, K1, 3, 2, K1, 3, 3, and K1, 3, 4, and K1, 4, 1, K1, 4, 2. And you may have a good idea that this should be also symmetric. Okay, so this is what it is. Now, again, I'm doing this just in order to put these components nicely in the system. So if now you look at the system we have on the right-hand side and compare how we want to, let's say, fill that into the bigger matrix on the left-hand side, you can see here this component, it goes to row 6, column 6. Okay, so that thing would come here. So that would be K1, 1, 1. Again, whatever that number is, we don't pay attention to. You can just take that number here. It's a coefficient times a number, okay? Times a number. You just do that. Okay, so that's K1, 1. Now, K1, 2, it's on the column 7, row 6. So that's K1, 1, 2. Then K1, 3 is on column 4, row 6. So that's here. And then this one would be here, 1, 4. You see? So it kind of is in a different order from what you have here. Here you have 1, 1, 1, 2, 1, 3, 1, 4. Now here you basically have 1, 3, 1, 4, 1, 1, 1, 2. Okay, so they find the placement based on the global numbering, not just the local numbering. Here you have the local numbering, obviously, it goes from 1 to 4, but here in your global system, they will look like that. So that's that. Then we need to do the same thing for the second one, or for the second row of the local stiffness. That would be then on column, on the row 7. So here. So that means a few components will be here, and we need to just find their places. And you can see their places are going to be on these 4 squares also, or 4 rectangles. And we will just do that. So on column 6, you have K21. On column 7, you have K22. On column 4, you have K23. And on column 5, you have K24. Now, before I proceed further, you already see that if you think about this is square, this is 6, 6, this is 7, 7. So this is 8, 8. So if you think about this line, that is your main diagonal of the stiffness. Okay. Now, if you remember about the values of these components, or you just look up here, they are all positive. Okay. So what you will see is that any value that comes to the main diagonal of the big matrix, they are only the positive values. They are the components that they were also on the main diagonal of the smaller system. Okay, this is a nice property or nice observation. So these 4, they come somewhere on this line. Okay, it doesn't matter which element. For every element, the main diagonal components come to the main diagonal of the bigger matrix, of the global matrix, and they are always positive numbers. Now, that means eventually on the global matrix, you always also get positive numbers on the main diagonals because you keep adding them, right? So for every element you add them, each of them is positive, so their summation is also positive. Now, that has a very, very nice property because it gives us a matrix or a system that we call positive definite. I mean, we know this is already symmetric, or we will see that it would be symmetric. So the big matrix also carries that property, but also later the system that we want to solve, positive definite. We will see that that little system, but by the way, this is maybe more important for the reduced system because that is the one we want to solve. So for the reduced system, we end up with a system that we want to solve where we actually deal with a symmetric positive definite system. Okay. So there is just a little, so I wrote 2 here. This is 1, obviously. One of you mentioned that, thank you. So that's that. Now, we play the same game for, let's say, the 3rd row of the matrix here. So again, the columns are basically the same 4 columns that you see here. Column 6, row 4. So basically, we are talking about this row, and now this column. Column 6, row 4 is K31. K31. Then column 7, row 4 is K32. Column 4 is K33. You see, it's not a complicated thing to do if you have the numbering right. At this point, it's something that I have mentioned this many, many times. It's something that, let's say, an intelligent person is not necessarily required to do it. Okay, so there is no intelligence here. It's just going through the numbers and indices and just put them in the right places. And as I mentioned, the advantage of doing this is that once you know, you don't have to be or let's say you don't have an intelligent person to do that. It means you can program it and your computer can do it for you. Okay. So the next one is then the last row, and that would be this row, and then again these 4 columns. So we are talking about these 5 squares here, and we are going to play the same game. So now here you get K1 41, K1 42, K1 43 here, and K1 44. All right. So if you look at what we have here, is basically also 16 components. So this is sort of the same thing or the same components, but at their right places. But as I mentioned, the nice thing or the nice observation you should have here, and I want you to pay attention to it, is that you can see that on the main diagonal axis or on the main diagonal of the matrix, you have the main diagonal component of the smaller matrix, which you know they are always positive. Okay, so these are always positive values. Another thing I want you to pay attention to is that this thing is symmetric. So if you look at these two, they are the same. If you look at these two, they are the same. If you look at these two, they are the same. Okay, and then these are the same. These are the same, and these are the same. Okay, so this also carries the symmetry. You see, it's a fairly complex story here, right? So the way that we took these numbers, it was a very strange process to find their numbering here. But eventually, if you look at the system here, although it has a different order, it still orders such that the symmetry holds, okay? So as I mentioned, eventually this symmetry and that other property of having positive components, they result in having a system that we call symmetric positive definite. And having a symmetric positive definite system or matrix, it means it allows you to solve it very efficiently and use it, let's say, optimization algorithms and minimization, or look at it as a minimization problem. Okay, so this was for element 1. Obviously, I'm not going to do it for all the elements. As you see, it takes time. I just quickly do it, for instance, for element 2, and then I show you basically how we proceed with the other ones. So I say I duplicate this slide. I'm going to remove this one, the previous one here. And then I want to do this for element 2. So I'm going to just remove each component and replace it by their corresponding, or let me just change the ones. Okay. So instead of the ones, we are going to have just number 2 here. So instead of each one, I'm going to just write 2. And then instead of this big one here, I also write 2. So that's your element number. But the global degrees, obviously, they are not the same degrees that you have here. We need to also adjust them. So we will go backwards. We will copy it now from the previous calculation that we had up here, and we just copy that, bring it downstairs again. So let's say this is your matrix. I copy that, put it here again. I make it a little smaller to to make it fit, but you get the idea. Okay, so now you see the components are one, or the global degrees are 1, 2, 4, 5, as you can see in the upper system. So I'm going to just write them here. Okay, so that means if I want to now sort of distribute that, a few components would be here, a few components would be here, a few of them will be here, and a few of them will be here. So this would be now the corresponding system. Okay, so the degrees, unlike the previous ones, they are not next to each other. There is a gap in between. Okay, so we want to just do that. Basically, we start again from the first one. So K11, it's 1, 1. K12 is just 1, 2. Then 1, 3, 1, 4 are in fourth and fifth column. So here you would have K11 of element 2, K12 of element 2. Then you have K13, K14. And then again, as you can see, these numbers, they are up here. And it just happens that they are all 0. But I don't want to write 0 because I want you to see it as a very general process. And that is exactly how you're going to program it. You just program it as their components, and then you calculate the stiffnesses locally, and they just replace those numbers. Okay, so those are the first 4. And then we come to the second column. Then it would be 2, 1, 2, 2, 2, 3, 2, 4. Then you have K31, 3, 2, 3, 3, 3, 4, 4, 1, 4, 2, 4, 3, 4, 4. Okay, so this would be basically the corresponding stiffness for this. But now, if you also look at it, we see the same story. These components, the main diagonal components, are these. So they are always positive. Again, 0, let's say, assume it positive, or at least it's not negative. So they are always positive. And as you can see, the main diagonal ones, they come here also on the main diagonal of the bigger system. And also, again, if you pay attention to this, this is symmetric. So K12 and K21 are here. And then on the, let's say, 4, 4 component of a big matrix, if you just look at it, it's these ones. So this would be, let's say, 4th row, column 1, and this is 1st row, column 4. Okay, so if you look at the 4, you see this, and then if you look at the same thing for the 5th, you see the same symmetry basically holds. Okay, so the big system is also always symmetric. All right, so let's say we play this game long and hard enough, and if you do that, again, you should do this again for just 4 more times. So we did it for element 1. We did this for element 2. You need to do the same thing for element 3, 4, 5, and 6. And eventually, after you have, let's say, all the 6 elements, you would end up with a stiffness matrix, which is semi-populated. It may have some zeros in it. So every component or every corner that you have nothing in it, it's going to be a 0. Okay. For instance, now I want to talk about those zeros before I finish this. And for instance, if we think about these 2, let's just, for the fun of it, let's just think about these 2 degrees. So this is on the first row, column 9 and 10. Okay, so let's go and see what are those degrees in our picture. So degree 1 is here. Degrees 9 and 10, they are there. You can clearly see these degrees, they don't have any connection with each other. Okay, if you had a member or a truss like this, then you may get non-zero components on those places in the matrix, right? But here you can clearly see that, let's say degrees 1 and 2, for instance, even 2, right? So degrees 1 and 2, they have nothing to do with degrees 9 and 10. So eventually, when you assemble the big matrix, I can, let's say, reassure that, or I can see it before doing it, that you will get zeros here. Again, this is not something you have to know or you have to necessarily have an understanding of, but it comes as a result. If you do the assembly correctly, at the end, when you get your global stiffness matrix, your global stiffness will have zeros here on these degrees. Okay, that shouldn't come as a surprise. That those zeros, they only mean that you do not have a connection between those degrees, and it's fine not to have a connection. Okay, so let me just say mind the zeros.
Ask something.
Yes, please.
Is there any chance we get zeros by two components canceling each other? Like maybe one of them brings something like 1 and the other brings something like -1, so it cancels.
Well, the answer is yes, but I am actually thinking, who asked this question?
Shimal.
So, Shimal, yes, the answer or the short answer is yes. And if I am not mistaken, I will just write this here, and if you want, you can check and let me know later. If I am not mistaken here, in fact, for the system that we have here, this component is going to be one of those. Okay. Again, I'm not 100% confident, but I think this component, which one was it again? This one. I think that component would look actually something like this. It would be 1 over 2 square root of 2 minus 1 over 2 square root of 2. So one of the elements, it gives you a plus, the other one gives you a minus, and then basically you get
Yes, I think elements 1 and 4 actually.
Yeah. So it might, again, I think if you look at the system, maybe it helps us better understand why. So that was which degree did I say? Degrees 4 and 5. So that would be, yeah, here. Is that right? Yeah, so on this degree, possibly you get something from this, you see? You get something from this, and again, possibly because of the symmetry, they will cancel each other, let's say in the x direction, something like that. Okay, so that's kind of what it means. Okay, so I think, well, again, the short answer is yes. For this system in particular, I think that is, for instance, a good example where this thing happens, and that basically means they cancel each other forces, something like that.
Okay,
thank you for the question. Did I answer the question?
Yes, that was exactly what I was asking.
Great, thank you for the question. Yes, so okay, so eventually you play with this, you do that, and then you end up with a system which is going to look, again, semi-populated. I don't want to say fully populated, because we usually don't have how populated has 1p or 2p's, I think. Okay, we usually have this thing that we call sparse. Okay, so we get a lot of zeros in our stiffnesses usually. So you shouldn't be surprised if you get lots of zeros. Okay, eventually when you have that, you can decompose the system into 5 pieces. You would get a piece here. All right. You get okay, so you get one there, one say here, one down here, and one on this side. So if you look at this, and now I'm going to use a thicker pen, you would eventually see your degrees of freedom, let's say on the corner here. So you would have something which is here. It's like degrees of freedom times degrees of freedom. That is always the size. Again, in this case, it happens to be 5 by 5, so it's not a perfect example really, but it's degrees of freedom times degrees of freedom. Then this is degrees of freedom times what we call degrees of constraints in this case. This one is degrees of constraints times degrees of freedom. So you may have a good idea it's why it is, or you may have a good idea on how to think about it in terms of symmetry, because let's say if one of them looks like this, the other one should look like that. Okay, so they should have different structure also, and then this one would be B or C times D or C. Okay, so you will basically have this sort of structure, and then again we called these KPU, KPP, KUU, and KUP. And the reason we did that, if you remember, was that because we wanted to basically get a system which looks like this. You would have your forces. You would have your forces, let's say in a vector. This would be your force vector. And then let me just duplicate the same thing. So we want our system to look like this. This would be your forces. So all the forces that are prescribed are up here. All the forces on the that are not known, let's say they are down here. Then on the stiffness, you get these 4 blocks that we just talked about. So this would be KPU, KPP, KUP, and KUU. This part is exactly as we did for a one-dimensional problem. So the system at this point, it has nothing new for us. It's this. And then all you have to do is to solve this system. And as we pointed out previously, we are going to do this using this so-called static condensation. So basically, we are going to just look into this part of the matrix. So that's what we want to do. And if you do that, you get this system. So you would have something like K, let's say PU as a matrix times UU plus KPP times UP, and all of that would be equal to FP. Okay. So let's say that's that. And all of it would be equal to your FP. And what you want to do next is to just take this one or this part to the right hand side. So you would end up with a system which looks like KPU times UU equals, so that FP minus, let me just copy paste this thing from up here, minus this thing. Okay, now if you look at just the superscripts here, you can just see P. Everything is P. That means everything is prescribed. So you know everything that is on the right-hand side. And basically, once you know that, what we call this thing, maybe as reduced system, then you can write it as something which looks like that. Let's say K reduced, maybe. So this is reduced system. And then maybe you can call this also U reduced. So this is like a reduced displacements, or these are only the unknown displacements, equals, and then let's call the right-hand side maybe, I don't know, small letter f. Okay, so that's a vector, that's all prescribed, and from that you can calculate the u's, the unknown displacements. Also, something interesting usually happens, or very often happens, these prescribed displacements, sometimes they are zero, okay? In many problems, they are zero, and we call that homogeneous boundary condition or homogeneous strictly boundary condition. If you look at this one, for instance, we apply a force, we apply a force, we apply a force. So we do not apply displacement. So all our Dirichlet parts are homogeneous. That means sometimes this thing is zero. And if that thing is zero, then this whole thing would be zero altogether. Okay, so you really don't have to even sort of pay attention to this or think about that part. So it's even a simpler system to solve. So eventually, you can do this, you can solve this, and I don't want to say it too confidently, but I think if you did this on your own and you inserted the numbers, you will find the the values that I'm going to write here for the displacements. So I'm going to just write those. So again, I'm not 100% certain about this, but you can check it. First of all, about the prescribed displacement, as I mentioned in this particular example, they are all zero. The unknown displacements, if you calculate, I think it would be something like minus 0.101, 0.353, minus 0.202, minus 0.2176, and the last one is 0.5533 or 30. Okay, so these are the ones that you calculate. Now, the prescribed forces also, I'm just writing them next to them, but these are the ones that you have prescribed. So it's not something that we need to calculate, but you can look at the system and see why they are prescribed like that. So you get 0, minus 2, 1, minus 3, and 3 is square root of 3. Okay, so for instance, let's think about these two, degree 1 and degree 2. Okay, let's look at the forces on those 2 degrees finally. So if you look at these are the 2 degrees. In degree 1, there is no force, right? So there is no force, there is no horizontal force. So let's say F1 is 0. In the second degree, there is a force 2 downwards. So F2 is minus 2. Okay? So that's why when you write those forces, you get these numbers. So the same holds for the rest of them. So you have this system, you have all the prescribed F's, you have all the prescribed U's. Then you calculate the unknown U's, and as I said, if I'm not mistaken, that is your final answer. All right, so we are done for this lecture, and not only for this lecture, as I mentioned, we are done for the first part of the course. So what we need to do from now on is to go to the second part. So this course, again, it has basically three main parts. And as I mentioned, usually I would like to think of them as 1/3 each. So in terms of what we want to do, we just finished, let's say, 1/3, and that is 8 lectures. So overall, I expect to have 24 lectures. What we want to do next is one-dimensional finite element method. So this is more mathematical formulation. The last one will be two-dimensional finite element formulation. And as I mentioned, the first part, let's call it spring combination. It's over. Okay.
Hocam, may I ask a question?
Yes.
Our condensed matrix is the one with KPU, right?
Yes. This one. This is the reduced matrix. You may call it the condensed matrix, but I would like to call it, this process is called static condensation, and I would like to call it the reduced matrix or reduced system. But I understand what you mean. Yes.
Okay, thank you.
All right, so static condensation is the process itself. Any other question? Well, if that's not the case, I thank you very much for your attention, and we will see us, or we will talk to us on Friday.